Welcome to the podcast. This is Mr. White,
And Mr. Johnson.
and today we're going to talk about reflected light
Need to.
in flat mirrors. So, what did they do in their investigation today, Mr. Johnson?
They were shining flashlights off of mirrors, trying to see where it actually hits on the table.
And that's an interesting concept because what I'd like to start with when we talk about reflection is when we discussed shadows, we discovered that light travels in a straight line, which is an interesting concept. It doesn't bend
Right.
around stuff. And so when we talked about shadow, for example, we had our light source, we had the object, and the light would be broadcast on the screen back here. And so it would be dark, but only in a straight line path from the edge of the shadow back to the light source, both top and bottom, which of course would be all lit up. And what we noticed is that the light didn't fill in back here.
No.
The darkness didn't curl out or anything. It's a very straightforward concept. And this idea that light travels in a straight line is helpful when we start talking about the law of reflection. So their law of reflection. So very to the point, we all know what a scientific law is. We need to define some things, though, because the investigation, I'm not sure if the vocabulary was as clear as it needed to be.
Okay.
So the first thing I'm going to draw is my mirror. There it is. Now, it's important that we differentiate and we identify, hey, this is a flat mirror, because next time around we're going to deal with curved mirrors, and light reflects off of them in an entirely different fashion. So what we like to measure, okay, is we like to say, hey, I got this beam of light coming in, and so we will call this the incident ray of light. And we need to know some stuff. And the easiest thing for us to know is to measure this angle. So if this is the incident ray, then this has to be, what angle does this have to be?
The angle of incidence.
Yeah. So the angle of incidence.
I know I should draw a dotted line.
Good point. So this dotted line, the one I'm pointing to right now, this is referred to as the normal. So remember back in the first semester, we described and discussed the normal force.
Yep.
What did we mean by the word normal?
It was the one that was going perpendicular to the surface.
Perpendicular to the surface, or 90 degrees to the surface. And so we're going to measure everything from the normal. Our angle of incidence is measured from the normal. If this was a laser or a beam of light from a flashlight or anything else like that, would the mirror absorb this light beam, or would it send it back?
Well, it would send it back.
Okay. And how exactly would it send it back?
Well, since you have the ray coming in at a certain angle, it's not that it's going to go straight back up. It's actually going to leave at the same angle that it came in.
Ooh. So it's going to do something like this.
Right. It's like it's bouncing off.
So yeah, this is what we call our reflected ray. And this must be, and they're going to have to, that's not quite right, so use your imagination, pretend they're the same. If this is the angle of incidence coming in, this must be the
Angle of reflection.
coming out. And you already said it, but these two angles have to be equal to each other. The angle of incidence and the angle of reflection are equal to each other. And the fact that light travels in a straight line predicts this.
Because it leaves in a straight line.
Yeah. These angles plus whatever you have left down here have to add up to equal 90 because we're measuring from the normal. Just a little heads up there. So that's the basics of what's going on. The two angles have to be equal to each other. There's some other things that I find interesting that maybe they can check out on YouTube or investigate a little bit on their own. As I stand in a mirror or in front of a mirror, I can see myself. My question is, does the mirror have to be as tall as me so that I can see all of me?
I would think not.
No. But there is a point of no return where I can't see all of me. What if? So let's just say, for fun, I'm 6 feet tall, even though I'm not even close. Okay. What if the mirror were only 5 feet tall? Would I be able to see all of myself? What if the mirror were 4 feet tall? Or if it were 3 feet? There's a point where I won't be able to see all of me. I'd only be able to see some of me.
Right.
So there's an object size versus a mirror size. And I don't think it's in the reading. And we're not going to talk about... I want to pose this question. How big does the mirror have to be for me to see all of me? And it does have to do with the angle of reflection and some properties of light. Things like that. I suppose the last thing we need to talk about today is what light is, or how light is made. Just a little basic talk. So you teach chemistry, right, Mr. Johnson? How is light made?
Well, it's a form of energy.
Okay.
Well, that's a good question. It's actually from electromagnetic spectrum.
Okay, so light, all kinds of light, by the way. There's lots of kinds of light. They range from X-rays, being tiny wavelengths, high frequencies, to radio waves, like the kind you hear on the radio.
Then you have gamma and
Yeah, there's some gamma in there.
ultraviolet. But then the light that you actually see, the light that we're talking about, is called visible light.
Right, there's the visible kind. There's the infrared and the microwaves. And so what you notice happening here is the energy gets bigger as you move across.
Right.
The frequency gets bigger as you move across. But the wavelength gets bigger as you move in the opposite direction. Okay?
Because we go back to the whole frequency of wavelength being
Inversely related.
correct.
Light is a form of energy. Light travels at a very special speed. We define it with c, and we round.
Right.
3 times 10 to the 8th,
Meters per second.
or 300 million meters per second.
Or for those of you that like to be stubborn Americans, 186,000
Miles per second. Stubborn Americans aren't stubborn, are
Oh, yeah.
they? No. So how is light made? Light is made by vibrating electrons. And we know that if light is a wave, and it is, that all waves are made by the vibration of something, some kind of matter.
Correct.
So in this case, it's just a vibrating electron. In sound's case, it was just vibrating matter. In water waves, it was a disturbance or a vibration of a water particle, or lots of water particles.
And by the vibrating electrons, what happens is that when they vibrate so much and they get to an excited state, they actually release energy, and
Right.
that energy is in the form of light.
And then the light, of course, we're going to really focus on the visible. Light comes in all of these different forms. X-rays take pictures of your bones. Gamma, they shoot at cancer cells. Not only does it kill the cancer cells, it kills
you.
the good cells. Ultraviolet gives you a tan or a burn. Invisible helps us see. Infrared, night vision. So those of you that play is it Call of Duty, is that one of those games?
Yeah, they don't have that this time.
No?
The new one, no.
No, I don't play those games.
Yeah, they don't have the night vision.
Okay. Microwaves are used in cell phone communications, but microwaves are strange because these are man-made. You can't point at anything in nature Nothing in nature is making microwaves. You actually have to generate these with a machine. And then radio waves are radio waves, FM, AM, some cell phone signals.
Right.
But most cell phones are microwaves. So we use this light in a variety of different capacities. And of course, we know that they vary in frequency, wavelength, and energy from our chemistry course as well. If we want to get into the vocabulary, light is a transverse, non-mechanical wave.
Non-mechanical.
Meaning?
That it's not made.
No.
No?
Meaning, what was mechanical? It's like sound is a mechanical wave. It has a requirement. If you don't have matter, you
Right.
can't have a sound wave. So the medium is called matter for sound. Water waves need water. But light waves are non-mechanical, so light waves can travel through
Anything.
nothing or anything,
Or space.
or just empty space. Non-mechanical means it can go through the emptiness of space. We know that light is a non-mechanical wave because the sunlight gets here through nothingness and gets here through our atmosphere.
You don't actually see it traveling through space either.
It's transverse because the wave is going to move to the right, but the parts of the wave are going to move up and down. Light sometimes is called electromagnetic. It's got two very distinct parts. It's got a part of the wave that goes up and down. Okay? That's the electric part that goes up and down. And it's got a part of the wave that goes into and out of the screen. That's the magnetic part. And I'm going to mess this up royally, but here we go. It's not awful.
That's pretty good.
And then it moves. Not great. It moves in that direction. So these waves go up and out, and then they go down and in. Up and out, down and in. And as they're doing this, as they're pulsating, then they're moving in the direction away from the source.
So an electromagnetic pulse is just basically an intense light burst.
That is correct.
That's in the game.
Oh,
They have EMPs.
okay. Wild. Okay. So this is what light is, and all these different light waves do this. So if we go back just for a moment, the X-rays, for example, they have the high frequency, okay, and the low wavelengths of light. You would have a whole bunch of these pulses in this section, but the radio waves would be way stretched out because of their low frequency, longer wavelengths.
So the higher frequency and the shorter wavelength, does that give X-rays the ability to actually go through and take those images?
Yes. So there's another equation, if you care. What we see here is that as the frequency goes up, the energy goes up. And the equation is not pleasant. It's E equals HF, where H is this constant that doesn't matter. But what we see here is if the frequency goes up, then the energy has to go up. There is no choice.
Isn't it Planck's constant?
It's called Planck's constant.
Nice.
Is that covered in chemistry class?
We touch upon it a little bit when we
Okay.
talk about photoelectric effect.
Right.
Just a little bit.
When light is not a wave but a particle.
Right, showing how the electrons are actually getting excited. You know Einstein. We got to throw Einstein in chemistry.
Okay.
You can't have them all.
Sorry.
Yeah, you can't have Einstein into yourself.
I'm sorry. But he was a physicist. He won 2 Nobel Prizes. Should have won 3. He was a genius. I kind of got a man crush on
Hey,
Einstein. So X-rays, because of their high frequency and high energy, can go through you and do damage. So can gamma rays. UV, we know UV has more energy than visible light. I look at visible light all the time. I feel fine. I get too much UV.
yeah.
Okay, my skin gets burned. My eyes don't do well with a lot of
No,
UV.
no.
High energy causes damage. People worry about cell phones giving them cancer. Let me help you out. You have nothing to worry about because they have low energy. Now, if you work at a nuclear power plant
Right.
and you're around gamma all the time, high energy, you got concerns.
So you can't become the Hulk?
No.
No.
No, body parts would be more likely to fall out than to be enhanced. That's my guess.
Would be cool, though.
it'd be something. Yeah.
Like if they don't watch this podcast, we could Hulk out on them.
We could Hulk out. So what they see is, they talk about cell phones and cancer. No way.
No.
Not enough energy.
Not even the students that use them all the time.
Right.
And if it did cause it, why would you have a Bluetooth that you sit in your ear right next to your brain the whole time?
I certainly wouldn't put my cell phone in my pocket next to me all the time. It would be on my desk, and I would use it, sparingly, as opposed to carrying it on my hip every day of every week, probably for the rest of my life.
Right.
I believe that covers light and all of its intricacies, and Hulk and Call of Duty. So
EMPs. I mean, they actually have handheld ones that they throw, like a flashbang, but you can actually mild radius for their electronic devices underground.
So signing off. This is Mr. White.
Mr. Johnson.